Okay, so in this other session we will see some other aspects of Xmipp and which are the protocols that are available that we have not covered during the introductory tutorial. So these are the protocols related to micrographs. We have seen all of them in the introductory tutorial. So this is as we have seen for letting the project to know that you have some micrographs, so this is called import micrographs. Then normally you would go to screen micrographs to make sure that your micrographs have the correct CTF, and then you may downsample them or not, depending on whether you want to work with smaller images, not only because of speed but also because of noise, because normally you remove noise and then all the algorithms converge much more nicely. Okay, so then we have also seen this manual supervised picker, particle picking. So here you open an interface where you can pick your particles manually, and then let's say that you have many micrographs, let's say 1000 micrographs. You have picked manually a few of them, 10, and then the 990 remaining you may pick them automatically. So for the automatic picking you are asked what is the manual picking that you have performed, and this is because here, while you are picking manually, we learn a model from you, so we learn what you want to pick and what you don't want to pick. So you need this model for automatic picking, and then you may pick two different sets. So one is, let's say you have a single import. So in this single import you have the 1000 micrographs. So you want to pick the remaining micrographs. So this would be micrographs to pick the same as supervised. So it is the same import data set. But let's say that you have done two independent imports. So in one of them you have already done the particle picking, and you have learned a model of what are your particles. But then you have an independent import of micrographs, so you may pick an independent set of micrographs. So you may use the model learned from this particle picking to pick in this other set of micrographs. So this is something very useful, especially if you have several microscope sessions. So in one of the sessions you learn to pick your particles, and then in the rest of the sessions that you have imported independently, you you pick your particles automatically, and then you can revise at the end through the analyzed results. You can analyze what are the particles that have been picked. You may remove some of them, you may add new particles. So this is one of the interesting protocols. Then we go into particles. Then you can extract your particles. Just let me repeat again one of the important issues here. You may pick only once, or you need to pick only once your micrographs, and then you can extract your particles at different downsampling factors. So you may extract at the same downsampling factor as you picked, and then here you can control the box size, or you can extract your particles from the original micrograph, so you pick only once, but then your particles are extracted at a different size, or you may extract at any other downsampling factor. So we did the picking at the downsampling factor 5, but then you can extract at the downsampling factor 2, and the suggested size for this other downsampling maybe this one, 249, that you may change to some more reasonable number. So this is a very interesting issue, because you have to pick only once, and then you extract your particles at any size that you like. Then if you are coming from another package, you simply import your particles. So you are asked for a metadata or for a stack file where your particles are, and then we ask you about the sampling rate, whether you want to copy the images or not, whether you want to import all the images or not. For instance, it might be useful just to import a few particles to make some test, or you may make a random selection of particles, etc. So this is the screen particles, in fact. So you may do a screen particles at the same time as you import them, so we can tell you what are the more normal particles and which particles do not follow the trend. So also you may do some pre-processing like dust removal, inverting constant, normalizing, etc. So other interesting protocols that you have here, pre-process particles. You need a set of input images. So let's say we take this one, the one we extracted, and then you may do a threshold. So for instance, here you select all the pixels below 0, and then you substitute those pixels by 0, or you may substitute by the average, or you may binarize the output images, or you may choose any other selection criteria. So let's say we don't want to apply a threshold, but we want to apply a filter. So you have bandpass filters, you have Gaussian filters in Fourier space, Gaussian filter in real space, and for each one of them you have a wizard like this, so that you can play and see what are the parameters that you like. So depends on you what you want to highlight from your signal, then you may choose a different parameter or the other. So again, we are not going to do a filter. What are the choices that you have to apply a mask? So you have different kind of masks, rise cosines, circular mask, or directly providing a file, a mask file that you have of your own. And here it is interesting to see this thing. For instance, you may design a mask as complex as you like. For instance, here you may let us organize like this. So you may draw your own mask, you see. So let's say this is my complex mask, and now I extract my mask here. I can save it as a file, save as, for instance, TIFF or JPEG are two file formats that we can easily read from Xmipp. So you may save them as TIFF or JPEG, and then at this point, let's close all this. So at this point, you supply this mask file, and then outside the mask you can substitute by 0 or the minimum value of the image or the maximum value of the image, the average or whatever. Also at this point in the preprocessed particles you may resize your particles, so this is changing actually the pixel size, or you may crop it. So cropping means what is the output size, so it may be smaller, it can be larger, so but the sampling rate doesn't change, so the pixel size is still the same. So the difference between resize and crop is that resize is changing the pixel size, crop is not. So this is preprocessed particles. You have an equivalent for preprocessing volumes. So also in volumes you have which are the volumes to process, which is the voxel size of the volumes, and then you have a number of options like changing the hand. This is computing the mirror of the volumes, or randomize the phases. So for instance, beyond 40 angstroms, so for details finer than 40 angstroms, you may randomize the phases. This is sometimes used to create initial volumes that are not biased by original information, or you may low pass filter the volume, for instance, by again details finer than 40 angstroms. You are removing them. You may put here whichever number of angstroms that you like. Then you may symmetrize, and here again I remind you, you have all the possibilities for the different symmetry encodings. And then for instance here you have when you symmetrize your volume, there are two possibilities. So for instance, let's say that you have a nearly symmetric volume that you want to symmetrize. Then what you want is to compute the different symmetrized volumes and then compute the average of them. But let's say that you have a part of your volume, for instance a part of the capsid of a virus that you want to symmetrize, and then you don't want to compute the average, but what you want is to compute the sum of all those symmetrized pieces. Then you may put a spherical mask, and for computing a spherical mask I need to have a volume selected. So as always you have this wizard that helps you to choose the right radius. Then you may adjust the gray values. So let's close all this. So adjusting the gray values, sometimes it is needed, because let's say that you have a volume that have some gray values. You have a set of projections whose gray values are not compatible with your volumes. There is a linear transformation of the gray values that transforms the volume into a volume that is compatible with the gray values observed in the set of projections. So here you would give a set of images with angles, and then this algorithm changes the gray values in the volume so that they are compatible with the gray values of the projections. Normally, if you have reconstructed with Xmipp, this is not necessary, but if you are coming from a volume taken from outside Xmipp, then you may need this. Then you may normalize the background or not, or so normalize the background sets the background to have 0 mean and the standard deviation 1. You may threshold, you may segment your volume, and the segmentation could be automatic, or it can be based on any voxel mass or amino acid mass or the mass in Daltons. And again you have here the resizing and cropping. So here you may change the voxel size of your volume, or you may change the box in which it is embedded. So this one is changing the sampling rate, this one is not changing the sampling rate. So some other interesting topics or protocols that you have here. Screen particles, we have seen it, is the process that you perform at the end of extracting. So you characterize your particles on whether they are normal or not. So it simply requires a set of images. So it will assign a set score. The smaller the set score, the more normal the particle is. Then you also have merging. So let's say that you have done 2 independent extractions of particles and you want to merge them into a single set. So you choose here one of the set of particles, the other set of particles, and the output will be a single set of particles with all of them. Then we have subset. So subset is an interesting one. So subset means, let's say you have processed your particles at the downsampling factor 5. So you have extracted small particles, you have processed them. For instance, you have done a classification, you have chosen the particles that you like in this classification, and then you want to extract, let's say, for instance, to put some numbers, you have 10,000 images from your extraction, and in your selected dataset you have just 5,000. For some reason you like this 5,000, but now you want to extract the equivalent 5000 at a different downsampling factor. So for instance, now you would extract to an independent extraction at a downsampling factor 1, let's say, so at the original size of the images. So this would be the full image set, so this would be 10,000 images at a full size, and then you want to make the correspondence between the 5,000 images that you liked and you found through 2D classification in this full set. So here would be the full set with the 10,000 particles. Here would be the set with the 5,000 particles that you like. So the protocol will choose from this data set which are the particles that correspond to these ones. It will produce a metadata with this list of particles. Then, yeah, we have seen all of this. So, which are the extra protocols that we have in here? So, for alignment and classification, we have all these choices. So, we have CL2D, ML2D, Kernel zone, rotational spectra, etc. So, the output of any one of these can be the input of the other. All of these protocols produce a metadata called classes.xmipp metadata, XMD, and you may open any one of them. So for instance, let's say these ones. Let's say we open this classification, then we may choose these images, save images as an images selection XMD, and they will be saved. This file will be saved in the same directory as where the original metadata is. So now we are saving 153 images. So let's say we save them, and now we can, for instance, take those images and give them images selection. So it is this file that we have just created. So we may take this file, this set of images, and reclassify using a different algorithm. So this is something that we normally use, and explaining the specificities of this 2D classification algorithm, it will be done in a separate tutorial. So the idea here to transmit is that you can reclassify your images, just make a group of them, and then you take this group and reclassify using a different algorithm. An important note about these two algorithms, Kernel zone and rotational spectra, they don't align the images, so they need them to be already aligned. If you have saved them as we have just done through the interface of analyze results of some classification, they are aligned. If they are not aligned, let's say that you have just extracted your particles and you want to align them. So you would use this only align. So this is asking for the set of particles that you want to align, whether you want to give an external reference or not, and what is the maximum shift that you expect from your images. And it will produce a single image, a single class. In fact, it is applying CL2D with one class, and it aligns all the images with respect to this class. So once you have them aligned, either because you have used this only align or because you have saved the particles from a classification algorithm, then you can go into Kernel zone or rotational spectra. Kernel zone is not parallel, and it takes time, but it is very useful when you use the mask. So let's say that we take this image selection, and we want to analyze specifically what is happening in one of the regions of the images. So let's say that we are interested in this part, let's say this part of the image. So we create a mask, we save it as we have seen before, and then we may use this mask to analyze what is happening in that particular region. And these are some specific parameters of Kerdensome. It makes a mapping of the original images into a 7x7 map, 2D map, so that neighbors in this map are topologically similar to each other. Okay, so these are for the alignment or classification protocols, and then we have also these two tools. So screen classes, we have seen it already in the tutorial, but it is rather interesting. So it takes a set of classes that you have computed using any of the 2D classification algorithms, and it compares it to a volume that you provide, and it computes the difference image and how similar the two are. So this is the maximum cross correlation between this image that is seen in the experimental data and this one that is reprojected from a volume. So they are sorted by cross correlation. So the worst correlating images or classes are at the end of this list. And here you have also a useful representation. So you have chimera, so you can see your volume, and then by rotating the volume, here we project the volume from the point of view of the user. So the projection, just looking from where you are, looks like this. So you may try to identify classes that you have in your dataset. Then you also have these denoise particles. So I have already done this denoise particles, and the idea is that you enter with some images. Let's say I have these images here. These are experimental images, and the protocol produces these clean views of those images. So this is the projection. This image here is the projection of the experimental image on a specific base that we will see now. So somehow it tries to extract what is the signal that is below all this noise. So it is a kind of looking at your particles in a different way. So probably you have lost a signal here, so you have lost small details that are present in your experimental images and that they have been lost in this projection. But otherwise, these images are much easier to look at than the original images where you barely see anything. So what is the basis? So the basis is rotational. It is in here. So the basis is this one. It is a rotational invariant basis, so that what it does, it takes all the images in your classes. So this needs a set of classes to be computed. So it takes your classes, rotate them 360 degrees, and then make a PCA of all this set of images. So this in fact has been published in a paper of Amit Singer, and this invariant or rotational invariant basis, it assumes that your particles have been already aligned. So you see that at the end of the basis, we compute 200 images in this basis. So the end of the basis doesn't have a clean structure, maybe a little bit here, but not so much. And then the important part of the basis is in here, that contains the important information of your structure. So we see here that the most important thing are differences in the capsid, and the difference between these two images is just a phased shift, like in here, you see. So most of the important bases are concentrating on the capsid. Okay, so remind, these bases assume that your particles have been already aligned, and once they are aligned, they can be projected onto these bases, and then you can check what is underneath all this noise. So it is a useful view. I wouldn't use these images for classification or for 3D reconstruction because they have lost small details. But otherwise, to look at the particles and to see if you have damaged particles or not, it could be useful. Okay, so we have seen all the tools that we have for 2D analysis, and then we may go into the initial model. So for the initial model, we have a number of choices. So let's say the most standard one now is Ransack. So Ransack, we have also seen it in the introductory tutorial, but it is important to review it again here. So it needs a set of classes. You may use, if you know that your particle is symmetric or not, then you may change the symmetry group here. The more symmetry the particle has, the easier it is to find the initial volume. And then this initial volume, normally it is empty, but you can use it to bias some random angular assignments that are performed by Ransack. So if you have an initial volume, this initial volume will be used to guide a little bit this random assignment. This is very much used, for instance, if you have a nearly symmetric particle. So let's say it is mostly C6, but it is not exactly C6. So here in the initial volume you provide a C6 volume, and here you put symmetry C1. So this C6 volume will guide the angular assignment, especially the tilt angle, and then the C1 will make the angular assignment to be totally random. Not totally random, it is biased by this, but to be random, sufficiently random, so that you can extract, you can recover your asymmetric structure. And then you need to provide the sampling rate. This is mostly because we do low pass filtering at the end. So the low pass filter, the cutoff frequency is computed as the sampling rate over the maximum frequency. So in this case it will be 1/5. So let's say your sampling rate is 3 angstroms, and then you want to filter it at 30 angstroms. So you would give these two values here. And remind, as we have covered in the introductory tutorial, that we take random subsets of your images so that for doing these random subsets you need to have enough classes. So if you have very few classes, then you better don't do this dimensionality reduction, and you take here the number of classes that you want. Okay, so we have Ransack. This is the most standard approach. Then the second most standard would be converting a PDB, and here we have a nice algorithm to convert from atomic atoms, from atomic coordinates, into a voxel volume. So here you would choose your PDB file. It must be a file, it cannot be a PDB code, and then you choose what is the final voxel size that you want, what is the box size in which you want to embed it, and if you want to apply a low pass filter. And here let's say you want to filter it at 30 angstroms, and here if you leave it as -1, the protocol will automatically determine what is the right size. Otherwise you may fix it if you want to 150 voxels cube, and then this would be the voxel size that you want from your for your PDB file. So this is the convert PDB. Then you have here simulated annealing. Simulated annealing is another way of trying to get an initial volume in which you give a set of classes, you give a symmetry indicator, and then you may bias or not the assignment. So it will randomly assign angles to the images, and it will change it, trying to make them to be as consistent as possible. This algorithm is very slow, so normally we don't use it unless we have a difficult case, and sometimes it can be used in combination with Ransack. In fact, in Ransack, if you go to Ransack, it is also in here, combine the Ransack results with simulated annealing. So if you have a case in which you see that the Ransack volumes may go to the incorrect orientation, then or to the incorrect volumes, then you may combine it with simulated annealing. It takes much longer, but normally it produces better volumes. Normally Ransack is the standard, and you don't need to combine it with anything else. And then you have random conical tilt. And random conical tilt, you need tilt pairs of micrographs, and you have to pick them in pairs also. So to pick a particle in the untilted image and then the corresponding particle in the tilted micrograph. So again, the specificities of this protocol will be covered in some other tutorial. Okay, so we have covered all the initial model. Then what about model refinement? So projection matching, we have already seen it in the introductory tutorial, and it is a way of making, if you have a starting volume that is reasonable one, using the experimental data to converge to a local minimum that in principle has a higher resolution. This projection matching is multi-reference, so in here, if instead of giving just one volume, you give several volumes, vol1.vol, vol2.vol, vol3.vol, then you are doing a multi-reference alignment. So the experimental images are assigned to one of these volumes, and then the volumes are updated and the process is reiterated. So alternatively, for 3D classification, what you have is the ML3D. So ML3D again takes the experimental images, and then you set how many volumes you want to start with, and this must be some different volumes. So for instance, if you want to classify into 3 classes, you need to provide here 3 different volumes. How to produce it? Let's say that you have reconstructed only 1 volume. How to produce the other 2? So you may go to the volumes, pre-process, and then for instance randomize the faces twice so that you have 3 different volumes. And here is the number of sheets that you may take one of these. For each one of the volumes that you provide here, you may split it into more classes, and again these parameters will be explained in some other tutorial. Okay, so ML3D is for 3D classification, alignment and classification. You have also the alternative of projection matching. You have also the possibility to call Relion from Xmipp, so you would also have a 3D classification. Again, this will be covered in a different tutorial. And then you have the identify outliers. So these identify outliers, it is here. I have already run it. So the parameters are a set of images. So normally it is a set of images that you have used for 3D reconstruction, and then a volume with which you want to compare it with. So for instance, I have taken here one of the volumes that we have obtained in projection matching, and then we ask you whether you have corrected the CTF or not for this volume, and what is the symmetry group. So the output of this is this classification here. So you have your image, and so all the experimental images that you have in your data set, and then for your experimental image we tell you which is the reprojection of the volume that is most similar to that, which are the angles and the shifts needed to obtain this image. And the interesting part is in here, where we compute the residuals of the image. So we subtract this image and this image to obtain this one here. So these residuals, in principle, if the image really corresponds to that volume, it will be just noise. It is not white noise because it has been colored by the CTF, but otherwise it is noise. It is colored noise. So from this color noise, or from this noise image, we compute the covariance matrix. So it looks like this, and we make some analysis of the covariance matrix, and we assign a set score to the covariance matrix. As always, the smaller the set score, the better the image is. So here, the more normal, let's say. So these set scores are more normal than the set scores here. Normally a standard threshold for set scores is about 3, and this comes from the Gaussian. 99% of the volume of a Gaussian is compressed between -3 sigma and 3 sigma. So here you see normally all these images are presumed to be pretty normal, and this set score is not normalized. There is a paper describing the set score, but again, the larger the value, the worse the image is. So these are worse images than those here. So this identify outliers is useful to identify particles that really do not match your volume. This is not the case in this example, but if you have particles that really don't go with your volume, you may identify them there. And this is under here, model refinement, identify outliers. So what other possibilities do you have in volumes? So here you have, for instance, create mask, and this create mask is rather rich. It has two parts. The first part, you create your mask, and in the second part you may post-process it. For instance, let's say that we want to create a mask for a volume, so we have to choose the volume we want to mask. So let's say it is this one. Then we want to apply a threshold, so to learn the appropriate threshold value, we may go to Chimera, and then we look at this value here. So now let's say it is this value that we want, about 0.03. So we take this value and we put it there, 0.03. So it will binarize your volume according to this threshold. And then once you have the binary mask, you may remove small objects, and the small objects are those that have less than 50 voxels, for instance, and you may change this value. You may keep the largest component that is connected. You may symmetrize your mask. You may apply a morphological operation, for instance, dilating the mask, erasing the mask, closing and opening. These two operations, for instance, they remove small areas, small black areas or small white areas. And then you may invert your mask, so whatever is 1 goes to 0 and 0 goes to 1. Or you may smooth the mask in the borders by convolving with a Gaussian of this sigma in voxels. So this is if you construct your mask using a threshold, but there are many other possibilities. For instance, you may segment your volume, and the segmentation can be done automatic. Many times it works. Some other times it not fully works automatically, cannot find the right threshold. Or you may use a number of voxels if you know it, or number of the mass in Daltons, the number of amino acids, or whatever. So some other possibility is that you construct your volume, your mask, from a geometrical description. So let's say that we want a spherical mask of radius 50 embedded in a box of 128 cube. So we give all these parameters here. Now we have the mask, and then we can still do the post-processing that we have seen before. Then here you have a lot of possibilities. So you can have a sphere, a box, a crown, Gaussian, whatever. So you may construct masks. This pre-process we have already seen. This resolution in 3D gives you more alternatives to the standard Fourier shell correlation. So normally during projection matching we just compute Fourier shell correlation. Here you may compute, for instance, differential phase residual. You can compute the structure factor. You can compute the spectral signal to noise ratio, or the volumetric spectral signal to noise ratio. So the volumetric, for instance, it is particularly interesting if you have an anisotropic distribution of particles. So in some directions you will have a better signal to noise ratio than in some other directions. So with this tool you can expect the signal to noise ratio in 3D Fourier space. Then you have also the aligned volume. So you have a reference volume and you have an input volume that you want to align to this one. And you may apply a mask or not to do the matching of the two volumes, and you may do the alignment in an exhaustive way. So in fact here you have the search parameters. So there are a number of rotations and shifts that you have to find. So all these parameters, we put a grid on them and we'll look for all possibilities. And otherwise you may do it in a local way. So let's say that you know that they are more or less aligned, but there is a small misalignment, so you may use the local search of the alignment parameters, or you can combine both exhaustive and local. All these possibilities, local doesn't take so much time, but exhaustive takes a lot of time. Otherwise you may use fast Fourier. Fast Fourier is an algorithm that has been done in collaboration with Friedrich Foster and Yuxian Shen, and it is pretty fast and it aligns normally the two volumes very well, but you need to compile Xmipp in a special way because you need some libraries that need some Fortran routines. So normally the Fortran compiler, we don't assume you have it, but otherwise if you have compiled Xmipp in this way, you can use the fast Fourier and it works pretty well. Then you have also helical parameters. So you may take an input volume that represents a helix, and then we look for the helical parameters, that is the shift that relates to equivalent positions of the helix and the rotation that relates these two equivalent positions. And you may give which is the radius of your helix, and you can also look for the hedral symmetry. Then and this protocol also applies once it finds the helical parameters, it applies it to the volume, to the input volume. So at the end you will have your symmetrized volume. Then you can compare your volume to a Sachs curves. So if you have your input volume, you have to give the sampling rate, and you can either compute the Sachs curve from this volume that is first converted into pseudo atoms, and then we compute the Sachs curve from it, or you may compare it directly to another Sachs curve that you have of your own. And here all these parameters all this SACS conversion and comparison, they are done through the program Crisol that comes from a package called ATSAS. So you need to have Crisol and ATSAS installed in your system to be able to use this protocol. Then we go to the extra protocols. This CASON protocol is you can create your own protocols. We have a web page in which we describe how to do this. So you create your own protocol and then you can run it through this interface. Then you have this flexibility analysis. The flexibility analysis tries to identify, let's say that your particle is flexible in a continuous way, so it changes its conformation in a continuous way. It is not just a discrete way of having two states, but it is a continuous movement. So you can analyze this continuous movement using these two protocols. This has been in collaboration with Slavica Jonic in Paris. And so first you compute the normal mode analysis. I have done it already for one of the volumes that we have here. So this is the bovine papillomavirus. So I have computed the first 20 modes, normal modes, and each normal mode looks a little bit like this. So this is the pseudoatom representation of the virus, and you see how the movement it represents, this normal mode, is a continuous movement. So this movement for the moment doesn't need to be represented in your images. We'll see later how to analyze this, but the idea is that the possible movements in your volume can be expressed as a linear combination of these movements that make a basis of the possible movements that you have according to normal modes. So you have different models, different modes. So you have here in fact a list. No, not here. Well, this is interesting also. This is how the volume has been approximated in two pseudoatoms. So you see in gray is the original volume, and here the balls represent the different pseudoatoms, and the color represents the intensity of the pseudoatom. So you see how we have approximated your volume by pseudoatoms, and then from these pseudoatoms we compute the normal modes. Here it is the list of modes. So we have computed 20 modes. The first 6 modes corresponds to rigid body movements. So they are translation or combinations of translations and rotations, and then the interesting modes are from mode 7. So here in the previous example we have seen mode 7. You can show any one of the modes you have computed. Normally, as a rule of thumb, you would like modes that are rather collective, because it means that the whole structure is moving, and the NMA score, normally you want it to be small. So the smaller the NMA score, the better, or the more global the movement is. So these are possible movements, and then the real movements are identified with this flexible alignment. So in the flexible alignment, you would choose the experimental images you have collected in the microscope, and then you would take the pseudoatomic representation of your structure, pseudoatomic or atomic. It can be applied to both, and then the set of normal modes you want to analyze, and the sampling rate of your images. And then you run this in your computer, and at the end what you have is what are the amplitudes, or what are the deformations that have been actually seen in your images. So it is not like in the previous example, the normal mode analysis. These are possible movements. What you have here are real movements that have been observed in the images. And for this also we are writing a tutorial of how to do all these NMA analysis, and you may also see the publication that we have with Slavica on it. Okay, so this is flexibility. Then for viruses, you can do this partial projection subtraction that it takes out the icosahedral part of your virus, so you can analyze the non-icosahedral part of your virus images. Then we have some algorithms for tomography, particularly for subtomogram averaging. For instance, this CL-TOMO is the equivalent of CL2D for tomography, and you only need to give metadata with the volumes that you want to align, and then the number of classes that you want, and there are some other parameters, but these are mainly the two most important ones. So in principle it is the same idea as in CL2D. It classifies first, or it aligns first all the subvolumes into a single structure, and then this structure is split over and over till you reach the desired number of classes, in this case 3. For doing this, you need to have this other part written in Fortran for a fast Fourier alignment of 2 volumes. So also then we have extended Xmipp to work with X-ray tomography, but this is out of the scope of this session. And let me comment on the different tools that we have here. So you have Image Operate. Image Operate is just an image calculator. So here you would have put an image, a volume, a stack of images, metadata, whatever, and then you can either add a number to them, or you may add another metadata or another stack of the same size, or you can do any calculation in here, like adding, subtracting, multiplying, dividing, computing the minimum between pixel by pixel. You compute the minimum between the two images, making the dot product, computing the logarithm, whatever. Then you also have here metadata utilities. So metadata utilities are meant to combine two metadatas or to do specific operations on metadatas. So you would have a metadata, and then you can make the union with some other metadata. You can do the intersection, join, disjoin. All these operations are described in the web page of the Xmipp metadata utilities. So the idea is that you can do many operations on your metadata, so that you can modify them as much as you like, and then go back into the analysis. And then also we have the metadata split. The metadata split is interesting because you can do here, for instance, you may take a large metadata of images, like a long list of images. Let's say you have 100,000 particles, and then you want to compute, for instance, the gold standard. So you take your 100,000 particles, you split them into 2 parts, and then these 2 parts you process independently, and at the end you compare the 2 volumes using this resolution 3D. So this would be a way of doing the gold standard in Xmipp. And otherwise you can split it in as many parts as you like, and you can play with them in different ways. Then finally we have all the tools related to EMX. This is the electron microscopy exchange format, so you can import micrographs from another package, and currently Bsoft and Eman are adapting their softwares to be able also to export and import in this electron microscopy exchange format. So you may import micrographs or particles and also export micrographs or particles to those packages. So in principle we have already reviewed all the possibilities that we have for analyzing particles inside the Xmipp, and as always these are the protocols that we have devised. Otherwise you may run your own scripts using any of the programs that we have. For instance, if you type Xmipp and you see the whole list of programs, there are quite a lot. So you can construct your own batches. In fact, what we suggest is that you construct your custom protocols so that you can use this framework to keep track of what you have done with your batches. So that's all. If you have any question, don't hesitate to contact xmipp@cmb.csic.es.